The future of quantum computing is one of the most exciting frontiers in science and technology today. While classical computers have transformed every aspect of our lives, quantum computing promises to go even further, tackling problems that were once considered impossible, unlocking new scientific discoveries, and reshaping industries. In this video, we will explore what the future may hold for quantum computing, the challenges it faces, and the revolutionary impact it could have on our world. At the heart of quantum computing are qubits, which can exist in superposition, representing multiple states simultaneously, and can become entangled with one another, creating correlations that classical bits cannot achieve. These properties give quantum computers the potential to perform calculations exponentially faster than classical computers for certain problems, from simulating molecules to optimizing complex systems. One major area where quantum computing is expected to excel is scientific simulation. Quantum computers can model the behavior of molecules, materials, and chemical reactions with incredible precision. This could lead to breakthroughs in drug discovery, energy storage, and the development of new materials. For example, simulating a complex protein or a new chemical compound that might take classical computers years to calculate could be done in hours or even minutes on a quantum machine. Another transformative application is optimization problems. Industries like logistics, finance, and transportation face challenges involving enormous numbers of variables and possibilities. Quantum algorithms, such as the quantum approximate optimization algorithm, can explore these possibilities simultaneously, finding solutions much more efficiently than classical methods. This could revolutionize supply chain management, financial modeling, and even urban planning. Cryptography and security will also see a dramatic shift. Many current encryption methods, such as RSA, rely on the difficulty of factoring large numbers, a task classical computers struggle with. Quantum computers, using algorithms like Shor's algorithm, could break these codes efficiently, prompting a move toward quantum-resistant encryption and entirely new approaches to secure communication. At the same time, quantum technology enables secure key distribution using entanglement, creating networks that are fundamentally secure. Despite the promise, the future of quantum computing faces significant challenges. Qubits are fragile, easily disturbed by their environment, and error-prone. Scaling up from tens or hundreds of qubits to thousands or millions, while maintaining coherence and low error rates, is a monumental engineering challenge. Researchers are exploring superconducting qubits, trapped ions, photonic systems, and topological qubits, each with its advantages and obstacles. Advances in quantum error correction will be essential to make large-scale, reliable quantum computers a reality. Hybrid quantum classical systems are likely to dominate the near future. These systems combine classical computers with quantum processors, using quantum devices to tackle the parts of problems where they provide an advantage. Even intermediate-scale quantum computers, known as NSQ devices, are already showing potential for practical applications in optimization, simulation, and material science. The quantum internet will also be an important part of the future landscape. By linking quantum computers across long distances using entanglement, it will be possible to create distributed quantum networks. This could allow multiple quantum devices to work together on a single problem, share quantum information securely, and enable global-scale quantum communication. In addition, quantum computing could accelerate artificial intelligence. Quantum algorithms can process and analyze massive datasets more efficiently, potentially improving machine learning, pattern recognition, and optimization in ways classical AI cannot. The combination of quantum computing and AI could open entirely new avenues in science, medicine, and technology. Industry investment and government initiatives are driving rapid progress. Companies like IBM, Google, Rigetti, and IonQ are building increasingly powerful quantum processors, while governments around the world are funding research, quantum infrastructure, and workforce development. Over the next decade, these efforts are expected to produce quantum devices capable of solving real-world problems at scales unimaginable with classical computers. The timeline for widespread quantum computing adoption is still uncertain, but the trajectory is clear. From experimental labs to commercial applications, quantum computing will increasingly influence science, industry, and society. It will not replace classical computers for everyday tasks, but for specialized problems, it could be transformative. In simple terms, the future of quantum computing is about harnessing the counterintuitive rules of the quantum world, superposition, entanglement, and interference, to achieve computational power far beyond classical limits. It will transform how we solve complex problems, secure information, and explore the universe at the smallest scales. Ultimately, the future of quantum computing is a world of possibilities. It promises discoveries in medicine, chemistry, materials, finance, artificial intelligence, and secure communication. The field is still young, but the potential is extraordinary. By continuing to push the boundaries of physics, engineering, and computation, quantum computing may redefine what is technologically possible and open a new era of innovation that changes everything.